Okay, everyone, thanks for making it back for our extra hour. It's been a while since we had one of these, but I was going through my notes, and I'm not going to cancel these no matter what. But, this is one of the things that COVID has made just hideously awkward. Not a lot I can do about it. I'm not going to cancel them. What I did was I looked through a bunch of old tests, and I see that I always ask a math question because you do so much of that. And I'm hoping that these are just free points. So let me give you an example of something I always put on the test. And it's relevant to what we just talked about just in the last hour. And again, I'm telling you, look out for this. Hopefully your skills in mathematics are good enough that this is not, you don't even need to study for this. So this is kind of good news. Now what I'm talking about is operator simplification. And you just saw an example of that in the last hour where I was changing the kinetic energy operator around using the product rule. Now the reason I'm doing that is because I have found many examples of the hydrogen atom Hamiltonian. If you're like trying to study via Google, you have to be careful because the hydrogen atom Hamiltonian can be manipulated using the product rule. It can be made more or less complicated and whatnot. So you have to be careful if for some reason you're looking these up, like I often am for like writing homeworks and exams and lecture notes. Sometimes I'll run into something and I'm like, that doesn't look right. And what it is a manipulation of the operator. Okay, now again, you just saw me do that in the last hour. It's fair game. This would be an early question on the next exam. It should be fairly easy. All right, now, let me remind you of something I did a while ago. And again, this is all operator manipulation. It's all about taking the kinetic energy Hamiltonian and transforming it because, maybe just for the hell of it, but number two, often that we can get to easier solutions. It's easier to deal with. And I'll show why at the very end of this. Okay, so let's take what happens when you turn double derivative of x, double derivative of y, double derivative of z, and you turn that into r theta phi, whatnot. You may recall that for 2D it was easy, but for 3D it was really nightmarish, and this is one of the first things that we had. Now, what I want to show is I am going to operate on this on a wave function, and I'm going to show that this can be simplified into another form. Okay, so what is this? Let's see. So what we're going to do is we're going to just call this thing, this is just the derivative. There's not a lot we can do with this. So what we've got is 1 over r squared ddr r squared, and let me use the terminology that, again, hopefully you're used to, the little dash to represent the derivative. So this is just just the derivative. Okay, now what? Well, now I've got myself a bit of a product rule, don't I? Let's see here. I've got, let's see. Let me do the wave function. Let's do the derivatives of the derivative. So that would be the double derivative. Here, let me use the same terminology. All right, so if I'm going to leave this one alone and do that one, that means I've got, oh, sorry, here, I'm a bit of a mess, aren't I? 1 over r squared. Leave this one alone. And I'm doing the derivative of the derivative, so that's the double derivative. And then I leave the derivative alone, and I do the r squared. There we go. And then I have to factor through 1 over r squared, and of course, what do I get? Now, I'm actually going to do a couple things here. What I'm going to do is I'm going to write out, I'm going to unfold this little terminology here, this dash as a double derivative, and I've got 2 over r, 2r over r squared is 2 over r, single derivative of the wave function. Okay, Now, the last bit. Every now and then, someone will mess this up, and that's kind of sad, because this is easy. Recall that I made this translation of this operator to this operator by applying a dummy wave function. What I'm going to do is undo that. All right, so here I've just got the operator 1 over r squared, just what I had before. Okay, so I'm just rewriting that without the wave function, and then you just rewrite this without the wave function. And it's just that easy. Now, I don't know why, but every now and then someone will get confused by that, and they'll horribly mess this up and get no points. So, again, you can literally just think of just erase the wave function. That literally is good enough to answer the question. But hopefully you see what I mean. Okay, now I've actually done this one before. So let's do another example, just for the hell of it. Okay, let's do 1 over r, double derivative, r, and let's see what that turns into. First, add a dummy wave function. Right? You never just operate on, without the idea that this is part of an eigenvalue equation, the solution to which is meant to be there. Not that you necessarily know what it is. Anyway, okay, now I said in the last hour, when I have a double derivative, to keep myself from messing up, I just write one of those down, and then I just apply what the heck happens next. Okay. So, let's see here. What have I got? I have got, let's see. I am going to do the derivative of one of these and leave the other one alone. So I just did r, and I'll let that one alone. Then I will leave r alone and do the other guy. And of course we know that let me use my shorthand because that's nice. Okay, so there we go. Next step. And I can see that I've got a product rule. So the product rule is how all of these questions work, by the way. So now I've got derivative here. There's no product rule on that first term. But now I've got a product rule on the second term. So what I'm going to do is do the derivative of r, which is nothing, just 1. And I leave that alone. And now I will do leave r alone and do the derivative of the derivative, which is the double derivative. Okay, so let's look at what this is. I kind of wrote these in a bad order. Let me do this. Let me write this last one first, which is double derivative of r squared sine of r. And I've got 2 over r single derivatives. And now, in terms of an operator, let me put down what I was dealing with to begin with, which is nice and simple, and point out that it is equal to double derivative plus 2 over r times a single derivative, which is exactly the same thing as this, which is exactly the same thing as, again, what you do when you are doing the transformation from spherical to Cartesian to spherical coordinates. Okay, so the point of all this is I've got a kind of a bloody mess. Every one of these operators is exactly the same operator, which, I mean, it is what it is. It's kind of annoying in all honesty, but it is what it is. And it turns out that when you do all your calculus manipulation to transform x, y, and z to r, theta, and v, you may run into this one first, but that looks like a freaking nightmare. This guy looks like it's a heck of a lot easier to deal with. So if they're the exact same thing, I'm going to choose this one. All right, now let me give you an example about why that's way awesome. All right, let's say that, again, imagine that you were asked to solve this problem. And I'll give you an example of why you might run into that. Oops, what's wrong with me? That's R. So here's an operator, right? And we know that when we apply the solution, the wave function, that since we're doing quantum mechanics, we should have an eigenvalue. So we have some kind of constant times the wave function. And so now you're asked to solve this, and I'm looking at that like, yeah, no, I don't want to do that. So instead, I plug this in. And while this is a trick in its own right, there's another trick I'm about to show you. Now let's make a little bit of a simplification. It doesn't matter, but it's just going to be way easier. Let's just say that this constant is 1. Let's just do that for the hell of it, and multiply through by r. So now, times r. Okay, so what you get is okay, so again, this is a neat math trick, because notice that on left and right, you're always trying to solve r times the wave function of r. Now, if you want to just look this up in an 18th century math textbook, you might want to do this. Let's find a new function called u of r, which is r times psi of r. Now, why would you do that? Well, here, let me make that substitution right here. My u's look a little funny, I know. So what you're looking for is the double derivative of a function equal to itself, right? So how hard is that? So you can imagine that that might be rather easy to solve. In fact, what it comes down to, and we'll just prove this, is that e to the minus r works just fine. So let's try that. Okay, double derivative e to the minus r is what? Is minus e to the minus r, which is e to the minus r, which is equal to e to the minus r. All right, so that works. So there you go, you've solved it. You haven't solved it, you're close. Remember, this is tricky. Psi, our wave function, is the solution. This is just like a proxy. It's like integration by parts. It's a placeholder. Therefore, the real solution is this thing over r, right? So it's e to the minus r over r. There you go. Right? Now you've got it. And now we can double check that. All right. So in fact, let's go back to the original problem. So I'm going to work the original problem, and without any of this substitution. I mean, hopefully you know it doesn't matter, but just in case you're not convinced, let me write out again. This u substitution gave us a differential equation that hopefully you're okay with dealing with these. I know you didn't have diffie-q, but come on, this is double derivative of a function equal to itself. And even if you're not comfortable with that, the solution is e to the minus r. So I'm going to go back to the original wave function and point out that the real solution is e to the minus r over r, and that comes about from this substitution right here. And it needs to be equal to a constant times itself. And the constant, we've already decided it was 1 just because that was easier. Okay, let's see, what is this? Now, when it comes to this problem, this gives me a real headache. So here's what I do. When I run into something like this, I write r to the minus 1. Okay, otherwise I'm just going to have a meltdown. I hate seeing function of x over x. I hate that. but I write r to the minus 1 instead, and this ends up being way easier. I'm writing all that down again. Okay, now I got to do the single derivative. Okay, product rule. I'll do r first, minus 1 over r squared. E to the minus, bring down minus 1 minus 1 is r to the minus 2. Okay, then I leave this thing alone. Okay, term number 1 done. Okay, next one. I leave r to the minus 1 alone and do the derivative of e to the minus r, which is just minus e to the minus r. Okay, I won't do too much algebra in a single place. Let's see, I've got e to the minus r, minus r, e to the minus r. That's from that r squared multiplying through. Okay, let's do the next derivative, which is minus, minus e to the minus r. God, this sounds like silly, but that's now positive. And now I've got myself a product rule, and let's see. I am going to do the derivative with respect to r first, so this has been canceled out. And then I leave r alone. I leave r alone and do the derivative. Do the derivative of e to the minus r. So that picks up a plus, all right, so that's canceled. And what you end up with is e to the minus r over r. So, which is r, e to the minus r over r is r to the minus 1, e to the minus r. So there you go. It's an eigenfunction with an eigenvalue of 1, which, again, we kind of forced that upon it here. So it's a little mathematically funky. I kind of fixed it to make it easy. But there you go. Now again, I would not have you do anything like this hard during the exam. Notice that it took me like 20 minutes, all right? So I'm not going to have you do this problem on the exam, but I do want to point out to you that if you can hack this, if you can do what I just did, then whatever I have on the exam is going to be way easier. Okay, so again, this was exam prep. Now, what I'm going to do next is I'm going to show you the real Schrodinger equation. So you can kind of tune out if you feel like. However, I want to point out to you that everything I've told you up until now has been completely false. I'm not kidding. I've been lying to you the whole time. I have never shown you the Schrodinger equation. I have been showing you a simplification of the Schrodinger equation. So, let me wipe out the board. And when you come back, I'm going to show you the real Schrodinger equation, which has time in it. And that's how I made those movies of those wave functions. I'm going to show you how I did it. Be right back in one moment. Okay, so I hope you stuck around for this. I hope you like this part. This is kind of cool, right? The real Schrodinger equation. This is everything we've been doing. This is not what Schrodinger derived. So what did he actually derive? Okay, so it's going to start out looking the same. So Hamiltonian operator, let's just, kinetic energy, we'll just do everything in X. Kinetic energy plus potential energy, I'll throw potential energy in there just for the heck of it, equal to energy times the wave function? No. Actually, remember when we were doing Planck distribution and we had the thing derived from Maxwell's equation? I know it was a while ago, but we had double derivative of x, y, and z equal to the double derivative with respect to time. That was the Maxwell equation for light in a box. And I said to you then, I know it's been a while, but I said to you then, that is very similar to the Schrodinger equation. It is, to the real Schrodinger equation. So this is the real Schrodinger equation. It has time in it. So you don't see e times the wave function on the right side like an eigenvalue equation. You get the time derivative of the wave function. Okay, so this is the real deal. Now, this obviously looks hideously different than everything we've been doing. And everything we've been doing, of course, has been Hamiltonian, of course, is the momentum operator, p squared over 2m, sorry, mass, right? I have to say mass from now on, plus potential. Now let's say that the potential is not dependent on time. It's rare to have a time-dependent potential. They do exist, but let's say that the potential is dependent on time. Oh, and tell you what. Let me let me spell all this out. The kinetic energy operator, and again, we're just going to be in one dimension. Equals, blah, blah, blah. Okay, so here's the thing. It looks like I've got the potential to have a separable solution, right? So whenever I have these differential equations, and I've got more than one variable, on the left I've got x, and on the right I've got here, I should have written this down. I've got the derivative with respect to time. So the idea is that if I can apply a wave function to both sides, all right, and the wave function is separable, then there's a wave function of position and a wave function of time. So there's two wave functions multiplied by each other. Now, there's two things to think about this. One is that this simply gives you a way to solve it. Two, like, if this is the real Schrodinger equation, what the heck have we been talking about the whole time? Because this looks terribly different. Well, here's a preview. It turns out that by separating the variables and getting to our miniature Schrodinger equations, what we have been working on the whole time has been a miniature Schrodinger equation only for like x. And then again, for y and z, don't worry about that. It's all the same. So it turns out time and position are going to be separated. Okay, so how's that going to work? All right, so what I'm going to do is I'm going to insert this into here, right? And then I'm going to, as usual, I'm going to divide out on the left, right? So remember this procedure. This will definitely be on the next exam. You have your operator. You operate on the right, and then you divide out on the left on both sides. And we're going to insert this the separated form, which remember that means that we've got one function of one variable times a function of another variable. Okay, so then what does that turn into? Okay, so let's see here. We are going to get, let's see here. On the left, we're going to have a wave function with respect to x, a wave function with respect to t. Now, let me, okay, again, I'm just going to do this just in x. And we all know that the x wave function is going to get caught by these operators, but the t one can pass right through. And what do we get on the other side? We get 1 over position and the wave function with respect to time. What have I got? I h bar. And I've got the derivative, single derivative with respect to time. So the time one gets caught there. But the x one can actually pass right through it. So I've got I h bar. Okay, so there we go. All right, let's simplify this. 1 over psi of x. All this stuff again. Double derivative. Is equal to I h bar over okay. Now, have we managed to separate? Bracket, need a bracket here. Have I separated? Well, let's see. Now again, if I had y and z in here, it would still work. These are all x's, and these are all t's. Okay, so separate terms. You can, if you want to see like how I tended to express it this way before, let's bring that over. Right. Okay, so an expression with only positions and expressions with only time. Now, that means that for one, the final wave function is of a separated form. So that's the number one thing you learn, is that this is the correct way to write the wave function. Now, you don't know what psi of x and psi of t are, but you do know that it should look like this. That's the first thing you learn. The second thing you learn is that each is a miniature Schrodinger equation. That is, they got to be constants. Each one has to be equal to a constant, because this constant minus that constant better be 0. Now, guess what? Guess what the constants are? The constants are energy. So this is energy minus energy equals 0. This was the idea of how it worked. So notice that if all of this is equal to energy, let me do my shorthand. I'll just call that H. So all that's H, right? I don't want to write all that out again. If all that's equal to energy, let's bring the wave function that was divided out on the left, let's bring it over. There you go. The eigenvalue equation, that's where it comes from, right? Okay, but we know that. We've spent an unbelievably painful semester doing this. Let's do the next thing. Now, E minus E. So we don't have to worry about the minus sign. What you get is I, H bar, derivative, and again, there's no x here, there's only time. So there's a wave function, it's all equal to E, and multiply it through. So it's still like an eigenvalue looking thing, just like the previous one. So there you go. So there's actually a time wave function. All right, let's figure out what this is, because now, as much as I know you didn't have diffie-cube, this actually doesn't look like that'd be that hard to solve. It's just derivative is equal to a bunch of constants, and let's see what we would get. I am going to, let's see, the first thing I'm going to do is I'm going to bring dt over here. Right? And now what I'm going to do is I'm going to take the partial of the wave function, I'm going to divide by the wave function, and over here I'm going to have minus IE over h bar. I use the fact that 1 over I is minus I dt, right? There we go. All right, so that's relatively straightforward. Okay, now what I'm going to do is I'm going to integrate each side. Now I'm going to integrate the right side over limits of time of 0 to time of, I'm just going to call it t again, from 0 to some time t. Now, you have to match limits. They have to work together. So on the left is the wave function at time 0, and the upper limit is the wave function at time t. Okay. I'll keep just working down. I know I'm not using the word super well. Anyway, so what do I get? Now on the left, that's the natural log. Upper limit minus lower limit. Now when you're subtracting two natural logs, you can actually divide ln A minus ln B is ln A over B. So that's why I did that on the right. And of course on the left, there's not much to it. It's just a bunch of constants. So there you go. Now I can take the exponential of each side and find that there we go. Okay, so now the next thing to note is that this is the wave function at time 0 Where you get that from is this thing, the thing that we've been doing the whole time. So this thing, remember that is the wave function in space separated from time. Well, by definition, you can just say that's the time equals 0 Schrodinger equation. The time-independent Schrodinger equation, you might as well just say that's the time 0. So if you solve this, you plug that sucker into here. Now, to move that thing forward in time, you just multiply by e to the I energy time, which time is something you would decide, like, okay, I've solved this, and that's at time 0. I want to know what it looks like a minute later. You just plug in 1 minute for time. Energy, well, you also would have to know that from here. And h bar is h bar. Now, if you're thinking like, well, I don't know how to handle e to the minus I something something, yeah, you do. It's cos argument minus I sine of the argument. Right? You can handle cosine and sine? Yeah, you can. It builds up some complex character, but regardless, we're good at that now. So what you see here, and I hope you think this is kind of cool, is that time-dependent quantum mechanics is actually kind of easy. It can get complex, but this isn't grad school. But this is the first thing I show grad students when we do time-dependent quantum theory, is I just show them exactly this. You can make this, right? And at first, it's really not, it's not difficult at all. Now, you recall how I had those little waves hitting barriers and how I time evolved a vibrational wave function turning into an excited state? This is how I did it. I started with the wave function from Wikipedia, and then I just multiplied it by this thing, and it evolved into, well, you saw what I did. So that's how I did it. Okay, so there's a bit of a break, and what happened is, in the time that I filmed what you were just watching to now, I developed some new videos, some more quantum time dynamic videos, and so I'm wiping out what I did before, and I'm going to show you that instead, which of course we're still on the same subject of the real Schrodinger equation, and I'm showing you how time enters quantum mechanics. So we've already seen how the time evolution is inserted in the Schrodinger equation, and what the real Schrodinger equation is. Now this is where this thing gets kind of interesting. All right, so let's think about, all right, we've been talking about hydrogen, and you know all the wave functions. So how does time play a part in that? And let's think about just a hydrogen and a 1s ground state. Now the universe is probably mostly hydrogen atoms, like in between galaxies and stuff. I don't know that, but I'm guessing that there's tons of just hydrogen gas floating around on its own. Maybe not all of it's in the form, maybe a lot of it's in H2, but some of it's just hydrogen atoms. And you can imagine, while, things are moving, galaxies will collide into galaxies, those take billions of years. And so at any given moment, all the hydrogen that's just doing whatever is not really doing anything at any given moment. Now, it turns out that all the stuff I've been talking about is actually consistent with that. Now, let me show you what I mean. Okay, so a wave function squared is the only thing that's really observable. So let's think about what that means for a time-evolving state. Now, of course, you got to remember that you've seen that the letter I is showing up in this e to the I energy time over h bar thing. So I need to be using complex conjugates. All right, so what does that mean for hydrogen? Okay, so let's do the complex conjugate. And let's say it's in the 1s ground state. Okay, now the part that's evolving time is over here. This is the complex conjugate because it's e to the positive I energy time. And now let's do the regular thing that we were just seeing. And non-complex conjugate. Okay, since these are functions, x times x times y is just y squared x squared, right? You can rearrange these things, but look what happens. Oh, sorry, that's minus sign, right? But look what happens when you combine these two, right? You get e to the 0, which is 1. So all you end up with is just the things that you've been learning that that we've just covered in this last week, just the same thing, absolute value squared. Okay, now the thing to notice about that, in all our writing down wave functions and graphing them and whatnot, up until today's lecture, you never saw t, you never saw time in it, right? So those are the time-independent states. Now, the fact that I am asking, well, what does a time-evolving state look like? And it says, well, just like everything else you were doing without time, it means that nothing's happening. So, again, as much as you maybe think like, wait, what? Here's my point. A hydrogen atom in a 1s state, ground state, floating up in the universe for billions of years, is for the most part not really doing anything. And this is completely consistent with that. There's literally nothing happening because there's no time in it. So that makes perfect sense. So I hope that that's kind of interesting in that, you know, just it shows that some of this quantum stuff, especially now that I've added a layer of complication, which may be like, well, I don't understand anything. Actually, you do. I mean, you understand why things don't happen. If you don't understand why things don't happen, then how could you understand anything? But yet, I mean, see, this was actually relatively simple. But now we got to talk about something else. And why do things happen, right? If you understand why some things may be completely static, then what about the parts that are moving, like me right now? Or, you know, why do chemical reactions occur? What happens when sunlight hits a molecule? Then things happen, and the wave function squared better have a time in it, because how else could things move? Okay, this is how it works. And it turns out that nothing is ever really truly in a ground state. And because nothing is truly in a ground state, you're not going to have time get wiped out when you do a complex, when you do the absolute value of a wave function. Now, at this point, I'm getting into grad school level stuff, so I'm going to simplify the examples. And actually what I'm going to do is I'm going to show you an example of quantum computing. And that's just because it's kind of a good example that's actually might be easier to understand than you think. Okay, so to do quantum computing, and also explain how do things evolve in time. And again, I've got these cool videos to show you. That's why I'm changing all this around from what I was going to do. Okay, what you may have heard that quantum computing is about superposition states. And that's when something is not really in a ground state. So let's write a superposition state for a hydrogen atom. So let's say something's in the 1s and a 2pz at the same time. Now notice that I've added the wave functions together. I didn't multiply them, I've added them, which I've shown you like, hey, don't do that. Well, we weren't talking about time evolution and quantum computing, were we? Right? So I've always been talking about multiplying wave functions for like x and y, but that was for a different problem. When it comes to how do things move, how do things evolve in time, and again with the example of quantum computing, this is the answer. Then you actually do add wave functions together. And remember that these are still functions of x, y, z, or r theta phi, however, you know, obviously r theta phi. And they would have the same r theta phi because I'm talking about the same hydrogen atom. All right, now, how do you make this? How does this come about? In terms of quantum computing, and if you had like a gas chamber, maybe I'm bringing up that little gas chamber again, what you would do is you'd use some really expensive lasers. You'd use high energy, ultra-fast lasers that can excite molecules into multiple states at once. So these have been around for about 30 years, and I think they won a Nobel Prize. Yeah, they did win a Nobel Prize. And what it allows us to do is to put things into two states at once, and that's what's called a superposition state. Now, in terms of why does the hydrogen move around somewhere in the universe, it's because something, instead of a giant laser in space that makes things move, actually, that's not such a bad analogy for the sun, isn't it? It's just not a laser. It's because things keep hitting other things, and light keeps coming off, energy keeps coming off from things like stars that whack things around such that they're not in their ground state. If they're in the ground state, nothing's happening. But because of the, things hitting other things driven by energy sources such as stars and nebula and all that, then things are not in the ground state and they evolve in time. Okay, now what you do is you can't do this anymore. So don't be writing this down. Okay, so you would like to evolve in time this way. Sorry, that's side 2. You would like to, as I was just showing you, evolve the state in time doing it this way, but you can't anymore. And again, if this was the answer, then you'd see that the result would not be dynamical. Now the reason that this no longer works is because you know that the energy is not defined, because if you try to put this into the Hamiltonian, when you add things together, you've got yourself a bit of a problem. All right, so the way to evolve this in time is energy is the result of the Hamiltonian operator. Since you can't just put in energy, you just put in the Hamiltonian operator. And now what's going to happen is, because this state, technically it doesn't work with the Hamiltonian, it actually is going to change over time. And I'm going to show you a little bit about how to do that in a minute. But for now, let me, I have to think about how this is going to work, because I'm going to have the videos later. What I'm showing you right here are 2 videos. Now, one is of a hydrogen atom in its pure 1s ground state, and that's on the left. And I'm going to evolve it in time. Now, on the right is exactly what I was describing before. It's a hydrogen atom in a 50% 1s, 50% 2pz. And I'm going to evolve that in time using that mathematics I just showed you above. Now, as time goes forward, you can see that it looks like the 1s state. It's like, what's happening there? It doesn't look like anything's happening. I am doing the mathematics. It's just that it's not changing, because it's not changing for all the reasons I just described. But the superposition state, you see that it's doing cartwheels. In fact, it's kind of fascinating to sit there and watch this thing go nuts. This is what I do at night, by the way, when I'm not chasing the cats. So you can see that the dynamics that drive everything, drove you to wake up and take this class, is happening right there in that superposition state. Again, this is fundamentally why things happen. And here's the mathematics that tell you how to do it. Okay, so there's that. I've got some other cool videos to show you in the next week on spectroscopy. Okay, now I told you I would explain a little bit more about how quantum computing works. It's just the example I wanted to choose, but that I wanted to show you here. Okay, so here's how it works. We see in those videos there was just a hydrogen atom. One was in the ground state, nothing happened. The other was in the excited state. So let's think about the one on the right. So it can either be in the ground state or excited state. So I'm drawing like energy levels. Now it can either be in one or the other, right? So if we're thinking about like computers, then this would be like a 0. Here, let me. So this is for that first hydrogen. And let's say that this is like this top state. If we're thinking about computing, you know that you have to have bits, and the bits are like 0 or 1. That's the only thing a computer can handle at the fundamental level. Okay, now the way quantum computing works is we're going to have a second hydrogen atom, and it also has a ground and excited state, and it can be 0 or it could be 1. Okay. So again, now I didn't put this in the video. I just drew one hydrogen atom. Sorry, not H2, but H number 2 and hydrogen number 1. So I have my little gas chamber, and there's 2 hydrogens in it, and I have that fancy laser, and I'm going to be able to do quantum computing. And that's by the way, that's how this stuff works. That's why quantum computers they're just building the first ones now, and they're going to be real expensive, all right, for reasons I'm explaining right here. Okay, now quantum computing. How do regular computers work? Well, I've got, this would be a 2-bit processor, right? One bit is either 0, 1, and the other one is also 0 or 1. And you can count to 4 with that, right? 0, 0 is 1, 0, 1 is 0, 1 is 2, 1, 0 is 3, and 1, 1 is 4. Okay, cool, so that's all you can do with it. And remember, I'm not trying to make fun of it, that's how our society works. All right, but here's the deal with a quantum computer. Now recall that there's only 2 pieces of information, 2 bits, in a regular computer. But from what you've seen about superposition and how it's dynamical, so it's real, the way that a quantum computer works is that it can take a coefficient of the ground state for the first hydrogen, and it has another coefficient for the ground state of the second hydrogen, and it can mix in an excited state of the first hydrogen atom. Sorry, what's wrong with me? Excited 1, and it can have some component of the excited state of the second hydrogen atom. Okay, so again, you've seen how I can mix these states. You can see how I can involve them in time. So I have 2 of these suckers, then I can write out the total wave function as comprised of 4 things, right? So here's my point. What I can do is imprint A, B, C, and D bits of information. That's my point. 4 bits of information, right? Now, normally you'd think there'd just be 2. I've got, 0, 1, 1, 0. Okay, so 2 bits of information that allows me to count to 4. But here I've got 4 bits of information from ostensibly the same thing, A, B, C, D, instead of 1, 2, 1, 2, 3, 4. So there's more. There's more muchness to it. Now imagine I have 3 hydrogen atoms, or 4. It turns out that the number of bits scales as the old number of bits to the second power. So you don't have to put too many processors or hydrogen atoms together before you outcompute a regular computer to an extreme degree. This is like a logarithmic scaling. And you know nothing, or exponential scaling, right? Nothing scales like exponential. So you don't really have to get too many hydrogen atoms talking to each other by adding their wave functions together before you've got a computer that's just mind-blowing. Okay, so anyway, so that's about it. I have a little bit of time left, so let me just show you one last thing here. As I mentioned, here, I'll go to another board. I mentioned that the way I made those videos was that I can't use e to the minus I energy. I have to use e to the I Hamiltonian t over h bar times the superposition wave function. So I want to show you something. I want to show you a little bit about how that mathematics works. Now, let's say the Hamiltonian. Now, we know that for the hydrogen atom, it's unbelievably complicated. We've obviously established that. Let's just say that the Hamiltonian, for the most part, let's go back to our origins, our first day of quantum, when the Hamiltonian is basically just some constants times a double derivative, right? Back to the simple times 6 weeks ago, which I know seemed like forever. So the question is, how do you do this? E to the double derivative, right? That's basically what I've got going on. Again, the Hamiltonian is simplified, but this is fundamentally what you're dealing with. How, in God's name, do you deal? To be honest, some of you have troubles with derivatives and double derivatives. What is an exponential of a single derivative or a double derivative? What is that? How can that even be, right? Because normally I'm used to, when I'm confronted with this, you take Calc 1, and you learn, power rules and all that stuff. Cosine is sine and yada, yada, yada. You learn all that. But how do you even deal when it's e to that, right? I mean, it's not in front of it anymore, so I don't even know what to do. Well, the trick is to get it back in front of it. And the way to do that is remember that exponentials can be written as a Taylor series, right? E to the x is 1 plus x. Of course, our x is now a double derivative. Plus 1 half x squared. And that would be the double derivative squared, which would really be a derivative 4 times, right? Quartet, I have no idea what the hell you call that. Okay, this is taking the derivative of the function. This is taking the derivative of the function 6 times, and on and on and on. Okay, and this, of course, is applied to the wave function, maybe like a superposition wave function, and as much as, yeah, it looks kind of complicated still, yeah, this is a little unpleasant, isn't it? It still looks a little complicated, but it turns out that if you go to, so I'm going to stop here, if you go to grad school, there's some mathematical tricks. I mean, these are a bunch of derivatives, but you can see the problem is that they just keep going and going and going and going and going. So how do you ever, like, really still make this work? I bet it's still a little confusing, but it's not, like, completely nuts either. You can certainly take a wave function and do a double derivative, and then do a double derivative of that, and then do the double derivative of that, and yada, yada, yada. In terms of getting it to converge, there's math tricks that you learn in grad school. But hopefully, I just wanted to show you that hopefully this isn't such a crazy foreign-looking thing. It's the kind of thing you could figure out how to do. Okay, well with that, I'm out of time. I hope that this was a fun lecture. You've seen the real Schrodinger equation. I've shown you some movies. I hope you like those. I've shown you a bit about how quantum computing works, which may be a big deal in the future. And spring break is here. Next time, for the next hour, actually we're going to do a test 2 review, just because that will help you mostly we're just going to do that to help you study for the final, which is really coming up soon. At this point, it's just basically 4 weeks away after spring break. And with that, I will see you all on next Monday.